Very well. So we made it into lecture 9. This is the second part of the gas lectures. And we have a few extra things to talk about involving ideal gases. Now, stoichiometry, which was the last topic of lecture 8, is going to be a pretty big part of the gas laws. But this lecture has a lot of extra information. Some of it you might have seen in previous chemistry courses, other one may be completely new. But I'll walk you through it all nonetheless, and as always, you are welcome to ask questions during office hours. All right, so what we're going to do is use the ideal gas law to derive some important values that tell you information about the gases themselves. We're going to start with something called the molar volume. All right, so the ideal gas law, PV equals nRT. I would recommend that you memorize this equation. This is a pretty ubiquitous equation within gases, and as you saw in the previous lecture, you can use it to derive any other gas law, and you can use it also to do stoichiometry, find the amount of moles of a gas, etc., etc. But what I'm going to do is tinker with some of the parameters in this equation to come up with other values. I'm going to concentrate initially on the volume and the number of moles specifically. And right here I can do either of two things. I can divide both sides by volume, or I can divide both sides by moles in order to bring these two parameters on the same side of the equation. Alright, now if I do divide both sides by moles, what I will need to do to keep only volume and only moles on the same side is to divide both sides by pressure. And this parameter right here is what we call the molar volume. And what I want to highlight right here is that the molar volume for an ideal gas, and I want to make that very clear, this is only specific to an ideal gas. The molar volume, which is given by V bar, is R times T divided by P, directly related to the ideal gas law itself. But another thing I want to point out, and this is perhaps the most important part, is that the molar volume itself can always be obtained by dividing the volume of a gas by its own number of moles. If you know the volume and you know the moles, you don't need to use the RT over P equation. In fact, this will only apply if you're dealing with an ideal gas, and for other situations that we're going to talk about in this lecture, using RT over P to find the molar volume will probably be incorrect and the bad approach altogether. But if you divide regular volume by moles, that will get you the molar volume itself. And I want you to keep that in mind for future problems. I'm going to have you do this a lot when we start talking about real gases. So volume over moles equals molar volume. All right, now if you look at a periodic table, and by now you might have noticed that yes, I am a little bit crazy about my periodic tables. Here's yet another one where I depict the molar volumes of all the elements at room temperature in their elemental state. And what you can see is that for the substances that we know to be the elemental substances that we know to be gases at room temperature, excuse me, the actual molar volumes tend to be relatively, in the vicinity of like the teens and maybe the 20s, right? But one thing that I want to highlight is that they're kind of close to each other, but they're not exactly the same. Substances that are solids, especially those that have high density, they have very, not super low, but low values of molar volume, meaning that they occupy little volume for any given number of moles. The gases occupy a little bit more volume for the same number of moles. That's why the numbers here are a little bit higher. Okay? Now, if I ask you for an ideal gas, or better yet, if I give you a problem that looks like this at first look may seem like you don't have any information whatsoever to do anything. But what I'm asking is for the molar volume of a gas being held at 10 atmospheres and 697 Kelvin. Alright, so I didn't tell you what the volume is, and I didn't tell you what the number of moles is. I didn't even tell you what the gas is either. So you have no choice here. You cannot actually find molar volume by dividing volume with n. You don't have those parameters. Here you have no choice but to use the equation that we derived from the ideal gas law, that R times T divided by P equals molar volume. We need to ensure that the pressure is in atmospheres and the temperature is in Kelvin. So, that being the case, we input the value of R, 0.08206 atmosphere liter per mole Kelvin, 697 for the Kelvin temperature, and 10 atmospheres for the pressure. So, atmospheres go away, Kelvin go away, and all that's left over is liter per mole, which are the units of molar volume. Carrying out the calculation, you find out that this molar volume is 5.72 liters per mole. And the one thing to notice is that you can easily change the molar volume of a gas because you can change the volume itself, right? You can compress a gas, you can expand the gas. So here we're actually dealing with a relatively low molar volume. That's simply because the pressure is ridiculously high. The temperature is hot, don't get me wrong, this is pretty hot, but the pressure is really high, and that's technically what's decreasing the molar volume. Alright, now a similar type of calculation involving the rearrangement of the ideal gas law is that of molarity. For molarity, we still focus on the number of moles and the volume of the gas. But instead of dividing both sides by n, now we're going to divide both sides by v. And we get rid of anything that may have remained on the right side of the equation, namely RT, by dividing both sides by those things. So divide both sides by RT, you end up with P over RT equals N over V. N being moles, V being volume, like liters. You have moles over liter, guess what? You found molarity. This is the concentration of a gas. And unsurprisingly, the concentration of a gas, the molarity of a gas, is nothing more than the inverse of the molar volume, right? Instead of having RT on top, now we have it on the bottom. Instead of having P on the bottom, now we have it on top. But now that's the molarity of a gas. And notice that both the molar volume and the molarity depend solely on the pressure and the temperature of the gas, nothing else. That's if the gas behaves ideally. Alright, so let's take a look at an example. We have a gas at a pressure of 540 millimeters mercury, a temperature of 400 degrees Celsius. We want to find out what the concentration of this gas is. We have no measure or mention of moles. We also don't know anything about the temperature, so what we need to do is use the ideal gas law to find out what these values would be. Alright, so the molarity we found out is pressure over RT. We need the pressure in atmospheres, however, and we need the temperature in Kelvin because the gas constant has units of atmospheres, liters, moles, and Kelvin. So the first thing to do is to change the 540 millimeters of mercury to atmospheres, and we do that by using the conversion factor of 760 millimeters of mercury in 1 atmosphere. Alright, dividing those two numbers yields the 0.711 atmospheres worth of pressure. The temperature, same idea. We have to add 273 to get the temperature in Kelvin, in which case we get 673 Kelvin. And now we go ahead and plug in the values. We have 0.711 atmospheres on top, 0.08206 atmosphere liter per mole Kelvin for the gas constant, and 673 Kelvin for the temperature. The atmospheres cancel out, the Kelvin cancel out, and what we have now is 1 over liter per mole, which is the same thing as mole per liter, also known as molarity. And as you can see, you can find the concentration of an ideal gas using the ideal gas law equation itself, although a little bit rearranged. Okay, in the next video, we're going to talk about molar mass.